Okay, it's me again, Franklin Hu, and we had discussed a little bit about the electrostatic field. And in case you all forgot, which I'm sure you did, I'm just saying that the electrostatic field is just a wave, an electromagnetic wave that's emanated by an electron or a positron. And that's it. That's my idea. I may be right, may be wrong. There may be problems with it, but it's just one way of motivating or try to explain or come up with any explanation at all why, say, an electron should repel another electron but attract a proton, having something to do with the phased waves. Okay, so that's one possibility, or it could be, say, Bob's G1, G2 particles. Could be that too. But we're moving on to the last question, which is what's the relationship to the magnetic field, okay? So what are we talking about when we're talking about the magnetic field? Well, we notice that we have things called magnets, and so I've drawn like a little magnet here, and we find that the mysterious property is that if we have our magnet, that the magnets attract each other. Right? So I have my magnet here, and the funny thing is that they seem to have different sides. So we by convention call them north and south. And so if you have a bar magnet, you will find a north pole on one side and a south pole on the other, and this is just by convention. Could have been, and you could have called it anything you wanted. You could call this Mickey Mouse and Goofy. It wouldn't have mattered. But what you find is that when the north side faces the south side, they attract. Okay? But if you were to put the south side against the south side, you would find they repel. Now this seems an awful lot like the electrostatic field and this attracting, repelling thing. But if we put but it's not due to you can't find a net positive charge on the south side and a net negative charge on the other to explain this. Furthermore, if you just put an electric charge right there, right next to the magnet, it won't move. I mean, it doesn't feel any force at all if you put just the electric charge here. So while the magnetic field might seem to have both this attractive and repelling force, it's clearly not the electric field, because I can put a charge right there and it will not move. It feels zero force. So this is kind of the mystery. We've got yet another attractive repelling force. And once again, the mainstream doesn't have terrifically good ideas on why this happens. So once again, a region, an area that is ripe for conquest by the critical thinkers, all right? So the question is, how are we going to explain this thing here? So we had come up with our list of things that any model should probably do, and probably the biggest thing would be explain maybe how permanent magnets work, but we also know that we can create magnetic fields by just using electricity. So if I take a nail and I wrap it with wire and I put a battery on that thing, this too somehow creates the same magnetic field, and if I put a magnet in the presence of this coil, it will act just like another ordinary magnet. So that's a mystery. So how can electricity, which is flowing charges, create this same force? And the things that are flowing in here are the same electrons that we think cause the electrostatic field. So that is kind of what one answer is, which is what's the relationship between the electric field and the magnetic field, which is apparently if you've got the electric field moving around in loops, this creates a magnetic field. But even in the simplest case, if you just have a straight wire and you connect that to a battery so that there's current flowing down this way, that if you have an electron heading this direction, it will get deflected in the direction of the flow. So that is probably the simplest action that we can think of for the magnetic field to take. And this is described by all kinds of crazy equations, most famously the Lorentz Force Law, where the force exerted on a charge is equal to the velocity of the charge with the cross product of the magnetic field. And the cross product is a really, really complicated thing. You have to break your fingers out and point in 3 directions to figure out what on earth is going on. So, a very mysterious force. So once again, the magnetic field, like the electric field, has a specific vector direction, and it has a specific magnitude, just like the electric field. But it seems to run in different directions. So the question is, once again, if we have to represent this physically, then there must be something physical to do it. Now, I had motivated that perhaps that thing is the neutron, right? I filled all of space with a neutron in my last speech. And what I'm thinking that neutron really is that it's probably more of a dipole thing. Now, some people think that the neutron is perhaps more of something in the middle with a diffuse negative charge, but I don't think that's the case. I think, once again, this is only my personal opinion, that this particle is a dipole, so it's negative on one side and it's positive on the other, right? So, in some ways, it would be a good thing to represent a vector, because the positive side can represent the pointy side, and the negative can represent the negative side. So, this thing can move around in 3D space any which direction you want, okay? Now, what I think a magnetic field is that in space which does not have a magnetic field, these dipoles are all randomly oriented, right? This is any orientation you can think of, just anything. But what I think a magnetic field is when you have a bunch of these and they're all pointing in the same direction, right? So the vast majority of them would all be pointing. There might be a few that are pointing in the wrong direction, but predominantly all pointing in one direction, okay? That's what I think the difference would be between space, which has a strong magnetic field, and space which does not have any magnetic field. In space with no magnetic field, these dipoles would be randomly arranged. Now the question is, so how does that make a magnetic field? So the most basic action of the magnetic field is to deflect incoming electrons, right? So if I have an incoming electron here, the question is, what causes it to deflect when it enters the magnetic field? And why does it deflect only if it's moving? Like I said, if I put a charge right there in the middle of my magnetic field, it feels no force at all. So let's check that. So if I put a charge right here, and it's like being pushed by 2 negatives, and so it's negative, so it's going to be repelled by everything. So in fact, in this particular thing, it's surrounded by negative charges. So it's not going to move at all. Okay, so that's okay, it's not moving, it feels no force. When I stick it right here, then it's between a positive and negative, so it might be a little more attracted to the positive. As soon as it gets close enough to it, it's going to stop. So it's not really going to experience any force. It just doesn't seem to matter where you stick charges in this dipole C. Generally speaking, if it's not moving, it's not going to really experience any forces, okay? So let's take now the case of a moving charge, okay? So if I'm seeing a moving charge, let's say it's coming down from this side of the screen. So, and I need to align my magnetic field so that everything is in fact aligned. So I'm going to put all the pluses on one side, all the minuses on another. So what's going to happen? I got an electron going down between here. Now it's going to, as it passes through these dipoles, it is going to see this positive charge on the one side and the negative on the other. So by Coulomb's force law, it's going to want to be attracted to the positive thing. But since it's moving, it can actually deflect. It keeps on going, but it's deflected by passing through this plus and minus. So can you guys see that? It's very simple. Now when it goes through and as it continues going through the dipoles here, it continues to see that same situation where there's a plus on one side and the same negative on the other. So as the electron keeps on heading through here, it gets a net deflection. It's basically just because it keeps on seeing the same dipoles all along the way. And the deflection is fundamentally motivated by just the Coulomb force law. So in that way, the magnetic field isn't kind of a force on its own. That it's just kind of a geometric arrangement due to basically this polarized dipoles that causes forces, an asymmetric force to develop on the electron. So that is the very, very basic idea that I described in my one-page paper, which is, how does the magnetic field, which is literally just this alignment, how does that alignment cause a moving electron to deflect through it? Now the other strange thing is that if you take a positron here, this is kind of the other difficult thing to explain, which is then that deflects in the opposite direction. Instead of going this way, it goes that way. Now why is that? Because when the positron goes through here, it sees the negative charge here, which it likes, and it sees the positive charge over there, which it doesn't like. So it deflects in the opposite direction. And this is one tricky thing about the magnetic field that you have to make work in your model. Because if you think that, for example, the magnetic field is actually a flow of particles around the magnet, then you could see, okay, then it will deflect the electron one way, or you would also think that it would deflect the positron the same way. If it's in a flow, it has to deflect every particle in the same direction. But if the thing that's doing the deflection is actually dependent upon charges, then it will do what it needs to do, which is it has the opposite reaction, right? So I think that's a very important motivating factor to say that the magnetic field has something intimately to do with charges in order to get this complete opposite reaction from these charges, which only differ by their charge, right? Yes, Bob?
Question. DC coupling through a transformer doesn't happen.
Yeah, coupling through a transformer happens.
No, DC coupling through a transformer doesn't happen.
Yes, it happens. I think it does. That's a magnetic effect. That's a complicated magnetic effect. Okay. But I think we have a lot of other questions to answer about this particular model before we get to that. Because I'm not 100% sure how induction works, which is what you're talking about. But maybe we'll get to that.
But it's still flow of particles through the field.
Well, it's a collapsing, and in order to get that, you have to have a sinusoidal, a rising and dropping current. But let's see here. But the other obvious questions I should probably say is, why should space align itself like that, right? Now we know that from the electric wire example here, like you have an electric wire here, and you have electrons, going that way. Okay, so what I'm saying is that when you have a wire, you've got electrons going all in one direction, that somehow that causes the charges to line up. Now this is a little bit speculative, but this is the way I see it. That as the electron charge comes this way, and it goes off the page, really any charge that's in this area will generally see the receding electron. So that will generally cause the positive side to go, aha, I see that guy leaving, I see all these guys leaving, and will generally basically comb the dipoles in alignment, kind of like flags in the wind, right? So you have flagpoles, and you have a wind blowing, they'll all point in the same direction. Okay? Now I'll have to admit this is kind of iffy because, charges can also see the incoming charges here. But I'm thinking that overall, because these charges can't instantaneously switch around, they can't look at that one and then immediately turn around, look at that one, and immediately turn around, look at that one. There's some lag that I'm thinking that in general, if you've got a bunch of charges all heading in the same direction, it's in general going to align all of the, like I said, these are like neutrons, I call them positive electrons as well, to basically all point in the same direction. And so this kind of explains why you have to have moving charges in order to have magnetic fields. That it has to sit there and comb this field so that's all pointing in the same direction. So that is one interesting thing that you need to explain. Now just to give a little background on some other alternatives to how this might be explained. So mainstream kind of has an explanation, and it's based on relativity. So I saw a video on this morning, and in fact missed getting off my bus because I was so fascinated by it. But what the mainstream says is that if you've got a wire, and that's basically a bunch of positive charges, and it's a bunch of negative charges, and so if you have some other charge over here, let's say a negative charge over here, okay. So there's not going to be any net force here, even if these charges are moving. Let's make the electrons moving here, right? Because overall the charge here is going to be the same. It doesn't really matter that the electrons are moving in this case. But what they say is that if you start this charge moving, then what happens is that you get a shrinking effect where the positive charges actually appear to be more closely spaced. This is like due to a length contraction thing. They appear to be more closely spaced, and therefore it causes a net positive charge to effectively develop on the wire, and that's what causes the electron to deflect towards the wire. Okay, now if I didn't explain that very well, it's because it's relativity, okay? But believe it or not, that is how that is explained. Another way to look at this is, like I said, other people literally think that the magnetic field is actually a flow of something around the current carrying wire. I mean, but I'll have to admit, it really kind of looks that way. Because I said the most basic thing that you see with the magnetic field is that that's a wire, and the current is going that way, and the electron is heading this way, the electron will go that way. So it's like the charge creates a wind, and that the electron is just getting blown into the wind, right? So that makes sense, kinda, except that when you put the positron in here, it gets blown in the opposite direction, right? And that doesn't make sense, right? So that's a great idea, except that it doesn't really explain what's going on with the proton. But we do have, I do think it's interesting because it's kind of a simplification for Lorentz's force law. So Lorentz's force law says force equals Q V cross B. Now I said that this cross B thing is really complicated because you have to take out your fingers and you have to say that if the electron is moving in where my first finger is pointing, and if the magnetic field is where my thumb is pointing, then the resultant force on the particle will be where my middle finger is pointing that way, right? You've got to do that crazy. So the force is not in any direction it doesn't seem to have any relationship to the actual where the particle is moving and where the field is, right? So you have to do this crazy thing to figure out what's going on. But I think that's probably because of the direction that the B field is defined. So if we have a magnet here, north-south, the B field is defined conventionally by what iron findings do. So they are defined in this direction, right? Now, me personally, I think it makes more sense to define the B field, the actual magnetic field, in the direction of the current that creates it. So if I have like a solenoid here, the wire's here, right? And that's just like a north-south magnet. That the field direction should actually be in this direction. And it's a lot easier to understand what happens to the magnets when they do that, because I have a YouTube video and I show that essentially you can treat like the permanent magnet as having a vortex around it, and that the charges will move in the same direction as the electric field that causes the magnetic field. So we have less this whole cross B business, right? And it could have been defined that way, but it's just that we conventionally define it this way. And apparently this is like curl or something mathematically. But that is one, I think, easier way of understanding what's going on with calculating what the force is. I think it's just a lot easier, instead of saying this, to say that the electron will deflect in the direction of the current flow that's causing the magnetic field. So I haven't done that rigorously, but I'm sure it ends up being the same. Now I suppose another question is, what on earth is a permanent magnet, right? Because we've got magnetic fields coming from coils, and then we've got magnetic fields coming from magnets. So what on earth is going on here? And I've only motivated an electron being deflected through a magnetic field, but what is really going on between, the opposite poles of a magnet? Because you put those in your hand, and they're pulling each other together, and I don't really know what's going on with electrons in here. So, but what I think is going on here is fundamentally within the magnet itself. I think there must always be current loop. Whenever you see magnetic field, must be current loop. There must be some electrons moving in a loop in the magnet. Now this kind of leads me to the conclusion that ordinary magnet is actually a room temperature superconductor, because it has to have these basically would have to be superconducting loops inside the magnet here. So, and we know if you make a whole bunch of little magnets, they can all end up being one big magnet. So that is one speculation that I make about magnetic, ferromagnetic materials, is that they are in fact a room temperature superconductor. And it would be kind of interesting that if we could take advantage of that property to make a much larger loop in these things, maybe as large as a whole wire, then perhaps you could come up with a room temperature superconductor, right? But for practical purposes, these superconducting loops form within the crystals of the ferromagnetic material. Now the question is, given that we've got these loops, these current loops, why is it that the magnets attract each other? Now, I believe the key is still this idea that the electron deflects. Okay, you've got electrons, you've got magnetic fields, and it deflects. Now the question is that what happens if that deflecting electron runs into a physical barrier? You know, like the boundaries of a wire. What's that going to do? It's going to actually push the wire down. Since the electron can't escape the wire, and if you've got a wire, it's got an electron in it, and it's being deflected down, it's going to cause the wire to push down. So I kind of relate this like the old CRT screens, where you have an electron gun, and it shoots electrons onto a screen, and they have magnets on here, and it causes it to deflect down. Well, suppose instead of electron beam, you had an actual physical wire there. And what would happen is that the electrons are deflecting down would actually shove the wire down. And if you were holding that wire, you would feel a force pulling it down. And this is actually how the basics of motors work, that if you send electric current through a magnetic field, I feel that the actual force you feel is actually the orchestrated action of all the electrons pushing on the outside of the wire. So in the case of the permanent magnets, you've got these loops here, and they're creating magnetic fields of an opposite nature. And so what happens is that all the electrons in this magnet are being compelled to move that way. And then all the electrons in the loops in here are being compelled to move this way. So what we end up is that we feel the force of 1 billion electrons trying to head at each other. Is what I would say is what we actually feel as the magnetic force. So it's just all those electrons heading at each other. All right. Okay, so I'm sure you have some questions about how or why this might work. I probably left out a lot of other things about the magnetic field. So you guys have any burning questions? Yes, Duncan.
Not a burning. Is this on?
Yeah, we can hear you.
Not a burning question, a complimentary question. Your concept of alignment seems to me to have a lot of merit to it. That alignment may not be because of positive and negative charges. It may be a result of the shape of ether cells, just as it is a matter of the shape of molecules and atoms. The vortices in light, for example, can be traced back to the actual shape of various molecules. This has been recorded. It's in one of my papers. Matter of fact, the latest one on entanglement, not the one I presented here, but the one on entanglement, gets into this at the atomic scale or the molecular scale, and there the strange things that can happen with, for example, the vortices of light can be traced right back to the shape of the molecules through which the energy is traveling. So thank you for the idea of alignment. I think it's an area worth pursuing. Another is what happens, that is related to alignment, what happens in a permanent magnet, for example. Well, in a permanent magnet, the iron is actually divided up into various areas.
Domains.
Domains, thank you. Searching for the word. And those domains, there's alignment in those domains. So you've got something there that is a rather positive indicator that your idea of alignment is it has got physical substance to it. Now, what is a permanent magnet? It seems strange because anything you would expect would run out of energy, but it doesn't seem to. Or if
No, it doesn't seem to run out of energy.
But it has to be getting that energy from somewhere.
Yes, it does.
And that energy, I suggest, is the energy that is in the field surrounding permanent magnets, which energy flows right through and continues as part of the energy of the permanent magnet itself. In other words, it's not something that goes on forever because of the magnet itself, but it's because of the combination of the energy that is flowing through a magnetic field continuously, actually flowing through the permanent magnet. An idea in any
Yeah,
way.
you bring that up, and I asked a question because this actually goes back to the whole question of what powers the electron, right? Because and what powers the refrigerator magnet, which you stick it on the refrigerator and it fights the force of gravity, all day long forever. That you think that take energy, okay? Now I'm saying that the magnetic field is entirely built out of the electrostatic field. So wherever it gets its energy from, I'm saying it's coming from the electrostatic field. Now the way I explain the power of the electrostatic field is that I said that my electrons, it has to emit these waves, right? Well, how can it do that forever? It would start doing that and then it would run out of energy and then be done, right? What I'm thinking is that these things are like little bells. We have our little bell, it's got a clanger in there, and when all these electrons bash into each other, they just ring, and they ring at their characteristic frequency. It's just, everything's got resonant frequency. So the energy comes in randomly, but it comes out at exactly one frequency and one phase. So I'm thinking that is the source of energy, just everything bashing into each other. So it's more like a box of ping pong balls that you're shaking violently. Or a box of bells. If I had a box of jingle bells and I just shook it randomly, you'd hear the characteristic frequency coming out of that, no matter how I shook the box, right? So, and that is sucking in energy from the outside world to generate that particular frequency. But once that happens, then it can go ahead and interact with the other electron here and cause the deflection effects. And it can do that as long as there's this ambient energy present. Which kind of begs the question of what happens if you take all the energy out of this thing? And we do that in experiments in ultra-cold physics, right? We create these Bose-Einsteinian condensates where we try and get the particles to be absolutely motionless. And we've never been able to do it. It always has to appear at some significant fraction above zero, because I think what happens is that I think they have actually reached zero, but when that happens, the bell stops ringing, the electron actually stops becoming, the Coulomb force drops off to zero, and it's no longer effectively an electron. And it effectively blinks out of interacting with anything in the world, so that it disappears. And actually, we do see some evidence of that in these Bose-Einsteinian condensates, that they'll take these rubidium atoms and they'll cool them down, and mysteriously some significant fraction just disappears. And I feel that's because you did get some of those rubidium atoms down to zero, these electrons stopped ringing, and effectively it fell apart. The atom just fell apart, right? So if you take that to the magnetic field, then the magnetic field is doing the same thing. It's just using the ambient energy that's around. We really don't detect that, if I stuck a magnet in this room, that it would cool the room down, but I think it would do so at some small amount. And then if you took your magnet and you did these ultra cold experiments, you would find that the magnetic field would drop. And actually they do see that they have done these experiments where it's like the magnetic field, as you cool a permanent magnet, it gets a little bit higher as it gets colder, but eventually it does drop. So that I would predict that would be the case, that as you get take any permanent magnet, put it in an ultra cool environment, that its magnetic field would drop. And if you could get it to zero, you would see that it would drop to zero because you've robbed the magnet of its actual power source. So that kind of motivates what is the power source for magnets and the electrostatic force, because you've got to answer that question. Where does it get the energy from? I mean, some people say that a magnet hanging on a refrigerator doesn't require any energy because it's not doing any work, but I think that's a bunch of baloney, and that it does take energy to keep the magnet continuously stuck on the magnet, as it does take continuous energy for an electron to continuously deflect any incoming other electrons or protons. So that's where I think the energy comes from.
Yes? Yes. There is never a vacuum in knowledge. There must be some explanation somewhere, somehow. I think you have provided some food for thought. I have a random question. Obviously, a neutral body will have an equal number of positive and negative charges. But why are electrons more mobile than positrons? For example, we have electron guns, but we don't have positron guns. Can you venture any explanation for this?
Only that for some peculiar reason. I mean, I think when the universe was born, it was generated with equal amounts of matter and antimatter, but it kind of depends on what you think antimatter is. So antimatter is anything which basically has the opposite charge. So the most basic piece of matter you have would be the positron, versus the electron. And if you had an antimatter proton, that would just be something which has a double, no, actually that would have a single positive charge on it, but would have a larger mass. And I believe that what the antimatter proton is that it would actually be, well, actually that's the opposite. That the antimatter proton would be two negative charges and one positive charge, so net is negative. And your proton is two positive charges and a negative. So this is what we see in the world. We see regular protons, we don't see antiprotons. But what happens is that all of the antimatter, which is strictly speaking the negative dominating charge thing, it ends up being stuck in the proton. So between the proton, you've got another negative charge flying around here. So all of the antimatter, which would be like the positrons, is actually accounted for in the proton. So there's no major imbalance of the missing positrons, right? They're just embedded in the protons. Now, I don't know why is it that our world is dominated by this thing rather than that thing. According to my physics, this thing should be as stable as that thing. It should be, the antiproton should be probably in high abundance, because that should be a totally stable object, but it's not, so that's really the only thing I can comment on that, really, so.
Could it be that we are in a part of the universe which is negatively charged, and therefore negative charges can fly about freely and not positive charges?
Anything's possible. Me personally, I don't think that, probably not. I'm still looking for some motivation as to why this is favored over that.
Well, there's a couple of things I would say. First of all, the electron and the proton, because we think in charges, and not necessarily, there are a lot of good models out there that charge isn't there. It's just a convention that we use. Well, first of all, I would say the nucleus, which is a proton, is in the nucleus. That's a very different beast in the universe than an electron, something that would orbit. So the idea of making an electron gun versus something that's making a gun of something that is the nucleus and the heavy part of really almost all the weight of an atom, those are really two very different things. I think the problem is because of George Washington, because over here, but Benjamin Franklin having put the positive and negative in the first place in history, that we have become so accustomed to that system that it blinds us to the ability perhaps of, let's not think of it as positive and negative, that these attractive forces must be of force, and therefore when we think of electrons and positrons, I think we're always thinking positive and negative, and many times in our head we forget that the difference between those two are great. It would be like the difference between a sun and a planet. You know, a sun is a very different beast than from a planet. So I would say, well, we don't have positron guns because that would be like breaking apart atoms and shooting just the nucleuses at. And that, that happens in space, in my opinion. A lot of people, you have free flowing protons. I have another question. So you're a question to you, Franklin. You believe in the Big Bang.
Do I believe in the Big Bang? I believe that I wasn't there, so I can neither confirm nor deny the Big Bang. Personally, I don't like it. I prefer that the universe has always been existing, and that things like electrons and positrons, once they are created, have existed forever. So that would be my preference.
Well, so you believe that the universe had a Big Bang, because you said several times in your talk about how it separated in the beginning and why there would be this balance and that balance. So that would indicate that you are a subscriber to the Big Bang.
No, that would kind of like motivate it as to if the universe was created. I would say that
You did say, it is recorded. You did say that when these things were produced, they fell into this. So the only thing I can say is then you're going to have to come up with something other than the Big Bang that created that division.
Yeah, and I would prefer perhaps the computer simulation model where God was playing with his gigantic computer, and he built it, and he's turned it on. And at that point, then the entire universe came into existence.
So so you believe that it wasn't here before and it's here now?
That would be one possibility. If the universe had a beginning and an end, then I would be in favor of saying that it was turned on instantaneously.
Oh, I'm just curious. So I'm still not clear. Are you believing that there was a universe and there is now? Was there a point at which there wasn't anything, and then there's the divisions of these particles? I'm still unclear.
I'm not so crazy about, say, the Big Bang idea, which says that all matter came out of a single point in time. That would not, like I said, I can't neither confirm nor deny that particular picture. I kind of think that it's a fantasy. So if you want to pin me down and say, no, I don't believe the Big Bang happened.
Okay.
And I'm not even sure if the universe was created, but if it was probably instantiated instantaneously in its current form.
Okay, I'm just trying to understand when you talk, and you said it several times, that the particles divided themselves into this quantity of this and that, and you were saying that was a happening that happened. So I was just trying to understand that phrase. I'm not here to.
Well, that happened in some unknown past. All we know is what we know right now, which is that we live in a world that contains electrons, protons, neutrons. You know, some people like to try and figure out what happened before that, or even if there was before that. Me, I would generally, like I said, I can neither confirm or deny what has happened in the past. All I know is what's happening in the current that generates the fields we observe. So I don't know, and if you ask me strictly where the electron comes from, I'd have to say, I don't know. So, but unfortunately we do think scientifically that the electron and the positron exists. So even I don't know where that thing comes from. A lot of theories try to motivate where the electron comes from, but I usually just say, we don't need to know where the electron came from because we know it's here already. So.
Okay, again, I was just trying to, you said that phrase the whole time. Another question I have for you is, you were mentioning that you thought magnetic fields were a flow, and then you wrote on the board the diagram that you had of the sort of neutron, which was a negative and positive. I'm imagining I'm just trying to understand your model, and that would be vibrating. So you have an electron vibrating in one way, a proton vibrating in another way in an ether, and that makes the positive attractions. And what I'm asking is that when you drew all those like cell kind of things with positives and negatives, you were talking about flow. Are you saying those cells are flowing around together, or
No.
make it? I was a little confused about when you say flow.
I may have confused you, but I'm saying that the concept of flow is wrong. That there's nothing flowing around a magnet. Nothing. Some theories think that there's flow, but I believe that is just wrong. So to not confuse you, I would say flow is wrong. There's nothing flowing around a magnet. What it is a static polarization of the dipoles around the magnet. Those guys, they just stay in there, kind of in place, all around the wire.
Okay, that cleared it up. I wasn't sure, right? Because in the beginning you were talking about flow.
Then you can explain something that kind of looks like flow.
Sure.
It looks like flow, except that the opposite charge flows in the opposite direction. But it kind of looks like flow. Maybe that's the confusion, because I'm saying that you can think of it like flow, but it's not really flow.
Okay, I got you. Okay, so I was just clear. So those things that you drew are stationary, right?
Yeah,
Okay,
those
gotcha.
things are stationary.
Okay, thank you.
Okay, any other questions?
Yes, please.
Yes, Muta.
There was something I was asked to consider, and let me pass it to you for your help and the help of others here, that an electric charge in the form of a spherical shell can spin and cause a magnet without requiring any energy.
Are you asking whether I think that's possible?
Yes.
Okay, well, this gets into the whole question of whether electrons have spin or not, I guess. Now, I suppose in my model, I would deny that. I would say that an electron is possibly, it's most likely to be a spherical object. But it could be, I don't know, anything that has a resonant frequency. It could be a sheet. It could be a triangle. It could be, it could be a string.
Let's consider it to be a spherical shell. Can it spin without requiring any energy?
I would say that, can it spin? Yes, it can spin, but I don't think that you would be able to detect a spin. So if you have a sphere and it's vibrating like a bell and it's rotating, I don't think you'd be able to tell the difference between that and the non-rotating case. And I don't think that, this is the other controversial thing, is that I don't think an individual electron can really generate anything as a magnetic field all on its own. Now, I know mainstream scientists say, yeah, we've measured this magnetic moment of the electron and stuff like that. But I believe that if the magnetic field is in fact has to be this structure that exists of many, many particles, right? The magnetic field can only exist as reacting to the incoming charge. Then inside the electron itself, If it's not surrounded by any of these other things, it can't possibly, on its own, create the field around it such that another incoming electron will deflect around it. It's just going to get repelled. It's not going to experience, I don't know, like deflecting kind of force like that. So that would be one of the more controversial things that I think, that basically when they measure electron spin, they're not measuring an inherent property on the electron, like for the experiment that measures spin, which is the one where they put it through the magnets, I forget, the Stern-Gerlach. They're actually using large silver ions to measure this, right? They're not using an individual electron to measure spin. They're measuring a property of an atom, not a property of an electron. Now, I have asked the question whether they've done a Stern-Gerlach with just bare electrons. You think they'd be able to do that? And, you know, there are some people who believe they've done that, but it's not something that's very common. You can take just a stream of electrons and sort them out into spin up and then spin down, right? You can do that with atoms, and I believe that is just it's just polarizing the atom, and which are slightly positive on one side and slightly negative on the other. And as soon as they hit the magnet, they will flip in one or two directions. So I think that can be classically explained. But I'm not a big believer in inherent magnetic spin, if that's what you're trying to get at. It just doesn't quite work with my model. All right. Any other questions?